Hello, sixth summer school, geometry summer school participants. Our final talk today is due to Michael Albanese. Thanks him for accepting our invitation. He's going to talk about a very interesting subject, Yamabe invariant of complex surfaces. Go ahead.
Okay, thank you very much for the introduction, and thank you very much for the invitation to give these series of lectures. So, as was mentioned, I'm going to talk about the Yamabe invariant of complex surfaces. So I just want to begin with a brief overview of what I plan to talk about this week, and then I'll give a rough rundown of what I'm going to cover in the lectures. So the objects which we'll be studying are compact complex surfaces. So it's called such as surface X. So these are complex manifolds of complex dimension 2. And what I want to do is look at these manifolds, these complex surfaces, in two different ways from two different points of view. So the first is via Riemannian geometry. So first, I forget the fact that this is a complex surface, and I just look at the underlying smooth 4 manifold. Okay, so just forget about the complex structure and just think of it as a smooth 4 manifold. Then there's an invariant coming from Riemannian geometry called the Yamabe invariant. Okay, and that's a real number that you can produce for any closed smooth manifold. But I can also view this compact complex surface from complex geometry, right? So complex manifolds, in particular, all the tools of complex geometry can be applied to it. So from the complex geometric point of view, there's another invariant called the Kadara dimension, which depends on the complex structure. And in complex dimension 2, it's one of 4 possible values: -infinity, 0, 1, or 2. So the question that I'm trying to address in these series of talks is, what is the relationship, if any, between these two quantities? So it may be unclear that there should be anything, because one is purely coming from Riemannian geometry. In particular, it doesn't depend on the choice of complex structure I've chosen, whereas the Kadara dimension a priori does. Okay, so it could be that I could have two different complex surfaces which have the same underlying smooth 4 manifold, but they're not the same as complex manifolds. So you would expect to have the same Yamabe invariant, but different Kadara dimension. Okay, so this question, it's not immediately clear that there should be an answer. A kind of spoiler alert, there is an answer, and I want to try and talk about what that answer is during this series of lectures. So in order to do that, today I plan to talk about what the Yamabe invariant is just in general for a smooth manifold. And then tomorrow, I'll talk about the Kadara dimension and more generally complex surfaces. And then in Wednesday's lecture and Friday's lecture, so there's no lecture Thursday, in Wednesday's lecture and Friday's lecture, I want to start talking about what some partial answers to this question are. Okay, so in particular, there was a result of Lebrun, who is my advisor, which gave an answer to this question for certain complex surfaces. And then in my thesis and work that's recently been appeared, we've tried to extend these results beyond the surfaces that he looked at to all complex surfaces. Okay, so, I've been to these kind of summer schools before and these series of lectures before. And personally, when I've, as a grad student, I found that it's, focusing on technical proofs is not very helpful. After all, if you want to see a technical proof, there is a paper where I can direct you. So I'm going to try and focus on the overarching picture and not so much on the technical details, kind of like just give you an idea of what's going on. So if you have any questions at any point, feel free to ask me, either, turn your mic on or put it in the chat. I'm happy to answer questions because, the first 2 lectures hopefully are just kind of general information about the Yamabe invariant and complex surfaces, which would be good to know even if you don't care in particular about this answer. Okay, but it would just be good information to know if you're interested in Riemannian or complex geometry. So I think those 2 lectures are probably the most important. So if you have questions, feel free to answer, and then we'll go from there, okay? All right, so let's start with the Yamabe invariant. Okay, so what do I want? So I'm going to let M be a closed smooth manifold of dimension which I'll denote by n, which is at least 2. And then I'll let REIM of M be the set of Riemannian metrics on M. Okay, so this is incredibly large space of all possible Riemannian metrics. So there's a functional called the total scalar curvature functional, which goes from the set of Riemannian metrics to the real numbers, where what you do is you take a metric and you integrate its scalar curvature over the entire manifold. Okay, so here, this is the scalar curvature. And this is the volume density or volume form if you're orientable. Okay, so basically, both of these depend on the metric. Okay, so you can think of this as a function on the space of all metrics. So this is also known as the Einstein-Hilbert functional. So of course, this is a thing you can do. It makes sense mathematically, but why would you do it? So Einstein and Hilbert kind of were interested in this functional for kind of physics reasons. So let me point out what those are. So Hilbert showed that the Euler-Lagrange equations of this functional give the Einstein field equations. In general relativity. So technically, this is with cosmological constant 0. So it's not important if you know what this means. I'm just giving a little bit of context. If you know what any of these things mean, fantastic. If not, there's kind of a physics reason for studying this thing. We're not going to use it. So let me just also point out that the Hilbert showed something else. So Hilbert showed that the critical points are Ricci flat metrics. So just like a function has critical points if its derivative is 0, a functional has an appropriate notion of derivative 0, right, which is related to these Euler-Lagrange equations. Right? And the metrics for which that's true are precisely the Ricci flat metrics. Okay, so there's some intrinsically interesting geometry going on here in terms of this functional. Okay. All right. So note, so you might ask, well, how does the value of this functional change if I change g a little bit? So note, one thing we can do to any Riemannian metric is rescale it. So if c is a positive constant, we could ask, well, what's the relationship between the value of the metric g and the value of the metric c times g? How are they related? So we can just look at, well, how does the scalar curvature change? Okay, so this is a computation you can do, hopefully only once, but you kind of do it once and you remember. So it's, if you scale the metric by a factor of c, you scale the scalar curvature by 1 over c. Okay. And likewise, the density scales by a power of c. It's n over 2, where n is the dimension. So that means that if I look at the value of the functional for c times g, that's equal to c to the n over 2 minus 1 times the integral of the original scalar curvature times the original volume. Okay, so rescaling the metric rescales the value by a certain appropriate power. Okay. On the other hand, if I look at the volume of my manifold with respect to a rescaled metric, I can see, well, how does that change compared to the volume of the original metric? Well, what is the volume? It's just integrating 1 times the volume density. So that's so likewise, the volume also changes by a power of c, just using the same information. Okay. So what we'd like to do is to kind of simplify this functional a little bit. We want to remove the dependence on this rescaling, because kind of from the geometric point of view, a metric and a constant times the metric aren't really that different. Okay, so what we want to do is normalize this functional so that rescaling by a constant doesn't actually change the values of the functional. Okay, so we can kind of forget about the difference between g and c times g. So what we're going to do is normalize it by combining our initial functional with the volume. Okay, so note that n over 2 minus 1, which is the power that I see here, is equal to n minus 2 over 2, which is equal to n over 2 times n minus 2 over n. So now n over 2 is the exponent I see here. Okay, so by combining these two in the appropriate way, I have the normalized Einstein Hilbert functional. Okay, which I'll denote by curly E, which again goes from Riemannian metrics on M to R, and it's given by, so I still have my total scalar curvature, but now I'm going to divide by an appropriate power of the volume so that when I rescale my metric, I get the same value of the functional. So it's going to be the volume of M with the metric G to the power of n minus 2 over n, where that expression is exactly coming from here. Okay, so you can check that with this appropriate power, rescaling doesn't change the value. Okay, so it's just like before, except when you rescale, it doesn't change anything. So alternatively, what you could have done is instead of dividing by some strange power of the volume, you could have restricted your functional to the Riemannian metrics of volume 1. Then that removes this possibility to rescale the metric, because if you rescale the metric, you change the volume. Okay, they're equivalent formulations. Okay, but because I wanted to look at the functional on the space of all Riemannian metrics, I just divide by this power of the volume. So let's do an example. So let's look at n, which is the dimension of M, equal to 2. Okay, so note that n minus 2 over n is equal to 0 in this case. So this exponent here is 0. So the bottom line is just 1. So if we take any metric on a closed surface, then the normalized Einstein-Hilbert functional is just given by the integral of the scalar curvature. Right? The denominator is just 1. So now what I want to note is that on a surface, the scalar curvature is twice the Gaussian curvature. So we have 2 times the integral of the Gaussian curvature. But by Gauss-Bonnet, the integral of the Gaussian curvature is 2 pi times the Euler characteristic. Okay, so I'm going to point out here, this is by Gauss-Bonnet. So we see that this functional applied to a metric G is independent of G. Right? So no matter what metric you pick, you always get the same value. So in dimension 2, this functional is just constant. It has the exact same value for every metric, and it's 4 pi times the Euler characteristic. Right. So this is a special case. So for n bigger than 2, this functional is not constant. Okay, so Gauss-Bonnet is an incredibly special thing that happens in dimension 2. We can't expect anything like this in higher dimensions. So this functional is much more complicated in higher dimensions. So I mentioned before that when we just took the total scalar curvature and Hilbert investigated that in terms of, Einstein field equations and so on, and he showed that the critical points of that functional are the Ricci flat metrics. So let's use EH for Einstein-Hilbert. So they're the Ricci flat metrics. He also investigated this normalized Einstein-Hilbert functional. So they're no longer Ricci flat metrics. They are Einstein metrics. So what's an Einstein metric? G is Einstein if the Ricci curvature of G is equal to lambda times G for some constant lambda. Okay, so the special case lambda equals 0 is Ricci flat. That's what happens in the unnormalized version. But when you normalize, you get this wider family, which is Ricci equal to a constant times the metric. Okay, so kind of, you can think of this is equivalent to the trace-free Ricci curvature, which is Ricci G minus SG over N times G. equal to 0. So the computation kind of goes along the same way, except in the first case, you get the vanishing of the Ricci tensor. In the second case, you get the vanishing of this trace-free Ricci tensor, which is equivalent to Einstein. Okay, so I should point out, if you want to know a reference for this fact about the critical points, so you can find this in Bess's book on Einstein manifolds. So theorem 4.21. Okay, so Bess is a good book. So a Ricci flat metric is a metric whose Ricci curvature is 0. Yep, so it just means that this Ricci tensor is 0. So remember, if you've got a Riemannian metric, it gives you a Levi-Civita connection. That connection gives you the Riemannian curvature tensor. And then if you take the appropriate trace of that tensor, you get the Ricci curvature. So it's Ricci flat if that trace is 0. Okay, you take another trace of the Ricci tensor, you get the scalar curvature. So Einstein is a generalization of Ricci flat. You can think of Einstein as constant Ricci curvature, and Ricci flat is constant equal to 0. Okay. So we started out with this Einstein-Hilbert functional, just integrate the scalar curvature. Then we normalized. We said, oh, well, if I just rescale the metric by a constant, that changes the value. So let me modify it. So that's no longer the case. I've kind of removed this dependency on rescaling. But no, if you have a Riemannian metric, you can rescale by a positive constant, but you can also rescale by a positive function. That gives you another Riemannian metric. So you might ask, well, what happens if I rescale by a positive function? So while the value of this functional doesn't change under constant rescaling, it does change under conformal rescaling. So we say metric G tilde is conformal to a metric G if G tilde is equal to U times G for some smooth function U from the manifold to the positive real numbers. So this gives an equivalence relation. On the set of all Riemannian metrics, we say two metrics are equivalent if they're conformally related. Okay, so it's symmetric because if G tilde equals U times G, then G is equal to 1 over U times G tilde. You can check transitivity as well. So we have an equivalence relation on the set of all Riemannian metrics, and the equivalence classes are called conformal classes. So a conformal class is just a set of metrics where you just get each metric by multiplying another by a positive function. Okay. So we denote the conformal class of a metric G by square brackets. All right, so my claim is that if you look at this functional and let it vary amongst metrics within a given conformal class, the functional is not constant. It varies, it can change values, but it's not completely arbitrary what it can do within a conformal class. Okay, so let me say proposition. If G tilde is conformal to G, then the normalized Einstein-Hilbert functional, its values aren't arbitrary, they're somewhat controlled by the value of the initial metric G. So the values are actually bounded below within a conformal class. Okay, so if you pick a conformal class, this Einstein-Hilbert functional, it has a lower bound on its potential values. So before moving on, does anyone have any other questions they want to ask? Maybe I'll give you a minute to catch up. So I'd like to briefly go over the proof of this fact, because it's not that hard. It's basically an application of Holder's inequality. So let me start with the proof then. Okay, so first I'm going to do the case n equal to 2, because as we've seen, there's something special about this functional in dimension 2. Then if you look at the Einstein-Hilbert, this normalized Einstein-Hilbert functional of the metric G tilde, well, we know that's, well, just by definition, the integral of the scalar curvature mu G. So note, remember the denominator is just 1 in dimension 2. But we saw before that that's just 4 pi times the Euler characteristic. In particular, that's the same if we have our original metric G. But if I have a function, that function is always greater than or equal to the negative of its absolute value. So that means the integral of this function is greater than or equal to the negative of its absolute value. Right? And that's exactly what you get here when n is equal to 2. So here, this norm here is the L n over 2 norm, which is by definition this thing. Okay, so if n is equal to 2, we've established what we intended to show. So in fact, we have more than this. We know not only is this functional bounded below on a conformal class, in dimension 2, it's just constant on the conformal class. It's constant for all the metrics. Okay. That's not true in higher dimensions, but in higher dimensions, we do have this lower bound. So that gives us some information. So suppose now that the dimension is bigger than 2. So I know that G tilde is a conformal to G, right? So I can write it as a positive function times G. I'm going to choose my positive function to be written in this form. So I'm going to choose a positive function U such that the conformal factor can be written like this. Okay, so it turns out this is a very nice simplification you can make to make calculations a little bit easier. Okay, so here, as before, U is a positive smooth function. So with this particular choice of conformal factor, the scalar curvature of the conformal metric can be written in a pretty nice way in terms of the original scalar curvature. So then there's a formula for the scalar curvature of the conformal metric given by u to the minus n plus 2 over n minus 2 LG U, where LG is some operator. So what is LG? Where LG is the what's called the conformal Laplacian. Given by, so it's a constant depending on the dimension times a Laplacian plus the scalar curvature times u. Okay, so just to be clear, what Laplacian do I mean here? I mean this one. dd star plus d star d, the de Rham Laplacian. Okay, so this is a messy calculation you can do, but it turns out if you have chosen your conformal factor to be written as u to this power, then you get this nice expression for the scalar curvature. If you just did it for g tilde equals u times g, the expression you get would be much worse, and the computation would be much more difficult. So it turns out this is kind of, in this setting, this is the nice type of conformal factor you want to choose, and you always can write it like this. Okay, so let's see how this knowledge of the scalar curvature of the new conformal metric allows us to prove this result. Okay, so let's look at what happens when we integrate the scalar curvature of the new metric. So now we have a formula for what the new scalar curvature is. So let's use that first. So it's u to the minus n plus 2 n minus 2 times the conformal Laplacian, which is given by 4 times n minus 1 over n minus 2 Laplacian plus scalar curvature of the original metric times u. So that's the scalar curvature part. What about the volume? How does the volume change? Well, we saw before that for a constant d mu c times g is equal to c to the n over 2 d mu g. But actually that works for functions as well. So if you have, say, let's use a different letter, let's say v times g, where v is a function, then we have the same relationship. Okay, so here the fact that it's a constant isn't special. You could just take a conformal rescaling, the same change happens in the volume form. So v function. Okay. So here the function we rescaled by was u to the 4 divided by n minus 2. So the volume changes by u to the 4 over n minus 2 to the power of n over 2. And then d mu g. Okay, so what I've done is taken this initial integral in terms of the conformal metric and written it now in terms of the original metric. So let's simplify this out a little bit. Okay. So I get 4 times n minus 1 over n minus 2 times u times Laplacian plus sg u squared d mu g. I claim that if you combine this with this, you just get a single factor of u. So let's check that. So we get minus n plus 2 over n minus 2 plus, we get 2n over n minus 2 equals 2n minus n is n minus 2, we get n minus 2 over n minus 2 equals 1. So that's what's happening kind of here, gives us this, and here gives us this. So if you put those powers of u together, you get a single factor of u, which is why there's an extra factor of u here, and this SGU became SGU squared. Now, by integration by parts, or rather Stokes' theorem, this can be rewritten because M is closed, just the L2 norm of D of U. SG U squared DUG. Right. Now, this first term is manifestly non-negative, right? So this is a positive constant. This is non-negative. So this is at least as big as SG times U squared DUG. Now, if you integrate a function, as we kind of did before, that's bigger than or equal to if you take the negative of the integral of the absolute value of the function. So this is minus this is nothing but the L1 norm of this function. And now I can use Holder's inequality. So here this is Holder's inequality. So I have P equal to N over 2 plus, and then Q equal to N over N minus 2. Okay, so note that 1 over P plus 1 over Q is equal to 2 over N plus N minus 2 over N over N equals 1. So that's why those values work for Holder's inequality. Okay, so we're almost there. So the only thing, so this is the term that appears as my lower bound in the proposition. So what about this thing? Well, that thing is actually, so note here, we didn't take the value of the functional, we just integrated the scalar curvature, so we have to divide by the volume. That's exactly what this term is giving us. So this is the integral of M. But this expression here, u to the 2n over n minus 2 d mu g, is exactly what we got over here for d mu g tilde. So this is u to the 4 over n minus 2 to the n over 2 times d mu g. The volume. And note, this is exactly the denominator that you would need for the Einstein-Hilbert function. So we see that so that implies that if you take functional applied to the conformal metric, it's greater than or equal to this thing here. So that's the end of the proof. So I promise not to do too many proofs, but I thought I'd do that one because it is once you know the conformal Laplacian, which is a good thing to know, it is just Holder's inequality. And it's kind of nice that all these exponents work out perfectly. Okay. So the point is that if we take this functional we've defined and we restrict it to a conformal class, say C, this is bounded below. So rescaling by a positive number doesn't change the value. Rescaling by a positive function does, but we have some information about how much the functional can change in a conformal class. It has a lower bound given by this expression here. So because it's bounded below, we define the Yamabe constant of C to be y of MC to be the infimum of all metrics in the conformal class of the functional. So we showed above, if you restrict the functional we defined to a conformal class, it's bounded below. So in particular, this infimum exists. Right? So note, these things are just real numbers. So we're just taking an infimum of a subset of the real numbers, a subset which is bounded up below. So the infimum exists. So we say a metric G realizes the Yamabe constant of a conformal class if, first of all, the metric is in the conformal class and the Yamabe invariant is equal to the value of the functional of that metric. So it's just saying the infimum is realized. Right? It's an actual minimum. So we call such a metric a Yamabe metric. So remember above, when we have these two functionals, the total scalar curvature and then the normalized Einstein-Hilbert functional, Hilbert had showed something about the critical points of those functionals, and they were geometrically interesting. So in the first case, we got Ricci flat metrics, those metrics whose Ricci curvature is 0. In the second case, we got Einstein metrics, Ricci curvature equals to a constant times the metric. So you might say, well, now that I've restricted my attention to the conformal class, are the critical points still just the Einstein metrics? So a priori, they might be different, right? If you take a function and you look at its critical points, like a real valued function, you look at its critical points, and then you restrict that function to a smaller domain, its critical points might change, right? So there might be a maximum where there wasn't a maximum before. So on the larger domain, this point isn't a maximum, but on the smaller domain it is. So the critical points can change when restricting the domain. So restricting our attention to a conformal class, do we still have the same critical points or are they different? So the answer is the critical points of this functional when restricted to a conformal class are the constant scalar curvature metrics. Okay, so no longer the Einstein condition. Right? So an Einstein metric does have constant scalar curvature, because if you take the trace of the Einstein condition, you see the scalar curvature is constant. But there are these potentially new critical points, which are scalar curvature metrics, which aren't Einstein. Okay, so you somehow pick up additional critical points when you restrict your attention to this smaller domain. So in particular, if I have a Yamabe metric, which is a metric which realizes this infimum, that means it's a minimum of the functional. So in particular, it's a critical point. Okay. So a Yamabe metric is a minimum of this restricted functional. So it has constant scalar curvature. So minima are in particular critical points, so they will have constant scalar curvature. So if this infimum is realized, it has to be realized by a metric whose scalar curvature is constant. So the issue of constant scalar curvature metrics inside of conformal classes is a very well studied problem, and it's a problem called the Yamabe problem. So
do you have an upper bound like spheres, Yamabe constant or something?
Yes, so I'll mention this in a sec. If you look at the Yamabe constant of a conformal class, then there's an upper bound for the set of all values of that constant.
Okay. Can you define the supremum as an invariant in that case?
Yes, that's exactly what the Yamabe invariant is. So that'll be an invariant of the manifold, whereas at the moment this is only an invariant of a conformal class.
Okay, right.
Yeah. So recall the Yamabe problem was to show that every conformal class contains constant scalar curvature metrics. Okay, so the history is a little bit complicated. Yamabe published a paper in which he claimed he could prove the full thing. Then later, particularly after his passing, Schrödinger showed that there was a gap. Basically, that corresponded to when the Yamabe constant is positive. And then later work of Aubin and then finally Shane showed that the answer is in fact true. So work of, let's see, what's the order? Yamabe, then Schrödinger, Aubin, and finally Shane. Shows that they always exist. Okay, so given any conformal class, you can find a constant scalar curvature metric. Actually, they showed more than that. They showed that every conformal class contains a Yamabe metric. Okay, so not only is it constant scalar curvature, but it's a metric which realizes this infimum. Okay, so this infimum that we've defined a priori is actually a minimum always. So the Yamabe invariant of a conformal class, which is defined as an infimum over all metrics in the conformal class, is actually a minimum. I can always find a metric whose value is equal to the infimum. So you might say, well, what's the difference between Yamabe metrics and constant scalar curvature metrics? So every Yamabe metric is constant scalar curvature. Is the converse true? So if the Yamabe constant of your conformal class is non-positive, then every constant scalar curvature metric is a Yamabe metric. Same is true if C contains an Einstein metric. So this is due to Obata in 71. But it's not true in general. That is, there are conformal classes C with positive Yamabe constant and constant scalar curvature metrics where the value of the normalized Einstein-Hilbert function is strictly bigger than the conformal Yamabe constant of the conformal class. So it doesn't realize the infimum, it's actually bigger than the infimum. There will be some other metric which does realize the infimum, but not all constant scalar curvature metrics have to do that. So there's something kind of different between Yamabe constant less than or equal to 0 and Yamabe constant positive. So what's the difference between these conformal classes? How should I think about conformal classes where this constant is positive versus conformal classes where the constant is non-positive? So I've got another proposition, but I'm not going to prove this one. It's not too bad. It's a slight modification of the proof before, but you need to use the Sobolev embedding theorem. So let me just state it. The Yamabe constant of a conformal class is positive if and only if C contains a metric of positive scalar curvature. Right. So the scalar curvature function is positive at every point. That's what it means for this Yamabe constant to be positive. Doesn't mean that every metric has this property, but there is at least one. Okay, so that's one way we can characterize these conformal classes which seem to behave differently to the general case. Okay. So let me say a few words about positive scalar curvature. So let me point out every closed manifold of dimension at least 3 admits metrics of negative scalar curvature. In fact, much more is true. You can remove closed and just take a non-compact manifold. It emits complete metrics of negative scalar curvature. And in fact, even better, it emits complete metrics of negative Ricci curvature. So in some sense, there's many of these metrics. They're easy to find. They exist in abundance on every manifold. Okay, so somehow the existence problem for negative scalar curvature or even negative Ricci curvature, it's really easy to find. Okay. This is not the case for positive scalar curvature. Okay, so for positive scalar curvature, there are huge restrictions about which manifolds can and cannot admit metrics of positive scalar curvature. And it's still kind of an open question to understand precisely which manifolds do and which manifolds do not admit positive scalar curvature metrics. Okay, so this is a topic of ongoing research. And this will kind of come up again later on. So it goes back to Lishnerowitz. There's a theorem for Lishnerowitz, then work of Gromov and Lawson, Shane and Yao, Hitchen, Stoltz, and many others, kind of Gromov more recently. There's lots and lots of work in this area to kind of understand which manifolds admit positive scalar curvature metrics and which don't. It's kind of a very delicate question. Okay, whereas in the negative case, it's kind of always two very different types of answer to a similar question. So you might ask, okay, that's negative scalar curvature and positive scalar curvature. What about zero, where it's just zero everywhere? Well, that's also related, it's intimately related to the question of positive scalar curvature. So if you have positive scalar curvature, then you necessarily have zero scalar curvature metrics. And so if you have a metric of positive scalar curvature, you can always find a metric of zero scalar curvature. If you don't have a metric of positive scalar curvature, then you have a metric of zero scalar curvature if and only if you have a metric of zero Ricci curvature. Okay, and then that kind of provides huge restrictions on the manifold. So kind of whether you're looking at zero or positive, kind of answering the question of, do I admit a metric of positive scalar curvature is very important and a very difficult one to answer. Okay, so these Yamabe constants, if we can show they're positive, that means we can in particular find a positive scalar curvature metric, which is not always the case. Okay, so some manifolds will have conformal classes where this is positive, some won't. Okay, but that's one indication of what's going on here, what's special about these classes. Okay, so as Mustafa kind of alluded to earlier, the values of these constants are not arbitrary. Okay, so you can't just find a value which is arbitrary. We've already seen that because for certain manifolds, it can't even be positive because that would imply a positive scalar curvature. But even beyond that, suppose you did have positive scalar curvature, you can't choose this to be any number. There are restrictions on what those numbers could be. So this is a theorem. Aubin, 76. So this is part of his work in kind of contribution to the Yamabe problem. So if you take the Yamabe constant of a conformal class on a manifold M, then it's bounded above by the Yamabe constant of the sphere of the same dimension. You take the round metric, the conformal class of the round metric. So this is the largest that constant can be. Everything else is less than or equal to it. Okay. Moreover, he characterized equality if and only if this manifold together with its conformal class is conformally diffeomorphic to the sphere with the conformal class of its round metric. So what does this mean? So not only is there a diffeomorphism, but if you pull back the round metric, that takes you to the conformal class we're looking at. Okay, so not only is M a sphere, effectively the conformal class you're looking at is the one of the round metric, kind of uniquely determines the value. Everything else is strictly less. Let me just point out an interesting corollary of this. So I'm not going to go through the details of the computation. Maybe I'll leave it as an exercise if you want to practice with this stuff. But you can use Aubin's result to construct examples of constant scalar curvature metrics which aren't Yamabe metrics. So I said before that such examples exist, but using this fact, you can actually construct them. So let me just outline how that goes. So let G be a unit volume constant positive scalar curvature metric on Sn. And let's denote its scalar curvature by S. So here I've just taken the round metric and rescaled it so the volume is 1. And I take G0 to be a unit volume flat metric on T M, the M torus. Then I let HT be G plus T, lots of G0 on this product manifold. So I have a family of metrics where T is positive on the product of a sphere with a torus. Okay, show. So using some of the facts we've talked about today, you can show that if I apply the normalized Einstein-Hilbert functional to this family of metrics, I get S, this constant scalar curvature value, times T to the power of M over N plus M. So in particular, for T large enough, this value is bigger than the value of this conformal class of the sphere of the same dimension with the round metric. Right, so this is just some finite number. As T gets larger and larger, eventually this thing will be bigger than that number. So we see that it cannot be equal to the Yamabe constant of its conformal class. Because if it were equal to the Yamabe constant of its conformal class, then it would violate this inequality that Aubin had established. So HT is a constant scalar curvature metric. And so if you look at the scalar curvature, you just find it's the same as the scalar curvature of the metric on the sphere. But it is not a Yamabe metric. Okay. So that's one result from Aubin, is it gives you a way to construct examples of constant scalar curvature metrics with arbitrarily high values of the constant scalar curvature, right? So this can be any positive number. So for each positive number, I can find a constant scalar curvature metric, and eventually that number will be too big, so it cannot be a Yamabe metric. It cannot be the value of the Yamabe constant of its conformal class. And you can modify this construction in various different ways. It didn't have to be a sphere, it didn't have to be a torus, but you can play around with that, get a larger class of examples that way. Okay, so that's one aspect of Aubin's result, but kind of the more important thing, and now we're finally going to get to the title of today's talk, the Yamabe invariant. So we've talked about the Yamabe invariant of a conformal class, but now I want to define the Yamabe invariant of a manifold, right? So not choosing a conformal class. So we define, so we have the Yamabe constant of the conformal class, we can have the Yamabe invariant of a manifold. Yamabe invariant of M to be y of m, which is just the supremum over all conformal classes of these Yamabe constants. Right? So it's the supremum over all conformal classes of the infimum of all metrics in a given conformal class of this functional. Okay, so by Urban's result, set of these values is bounded above, so its supremum exists. So this will always be finite, it will always be a real number. So that's the Yamabe invariant of M that I kind of mentioned at the beginning of the talk with the overview. This is the one of the two invariants we're going to be focusing on. So this depends only on the smooth manifold M. And so in some sense, we're computing a number by looking at all possible Riemannian metrics. First, we look at them within a given conformal class, compute a bunch of numbers that way. Then we take those numbers and we consider all of them together to compute the Yamabe invariant. Okay, so there's no dependence on any metric or any conformal class here. It's just a number we produce associated to a manifold, closed smooth manifold. So let me tell you a little bit about this invariant. So first, this is a diffeomorphism invariant. So two diffeomorphic manifolds have the same Yamabe invariant. Note that it's positive if and only if M admits a positive scalar curvature metric. Because if the supremum is positive, that means there's some conformal class which is positive. And as we saw above, a conformal class is positive if and only if it contains a positive scalar curvature metric. So this number we produce associated to our manifold can be used to answer the delicate question, does my manifold admit positive scalar curvature or not? So if you could compute this, you can check, is it positive or is it not positive? That will answer the question, does it have positive scalar curvature or not? Okay. So it follows so we have that this invariant is a diffeomorphism invariant, but it's not a homeomorphism invariant. So precisely, so there are closed, smooth manifolds, M1, M2, which are homeomorphic, but they have different values of the Yamabe invariant. So you can view this as either a good thing or a bad thing, depending on your point of view. So on the one hand, you could view it as a bad thing because you need to know what is the smooth manifold. It's not just enough to think about the underlying topological manifold. If it was a homeomorphism invariant, it wouldn't matter which smooth manifold structure we picked. So for example, theorem of Milnor shows that there's more than one smooth structure on the topological 7th sphere. So a priori, this invariant might be different depending on which smooth structure you pick. Okay, so that's kind of, oh, maybe that's a bad thing. It's harder to compute. On the other hand, it could be viewed as a good thing because, well, maybe I have two smooth manifolds and I know they're homeomorphic and I want to check, are they diffeomorphic or not? I can try to use this invariant to distinguish the two manifolds. Maybe they are homeomorphic, but they're not diffeomorphic. And the way I can show that is I can compute the Yamabe invariant of one and show it's not equal to the Yamabe invariant of the other. So it's a tool I could use to distinguish homeomorphic manifolds, which aren't diffeomorphic. Okay, so it depends on your point of view. I like to think of it in terms of the second way. Right, so in particular, you can view, so taking this kind of second point of view, you can view y of m as a real valued refinement of the Z2 valued invariant P of M. So it's only got two values. It's 1 if M admits PSE metric, and 0 if M does not admit PSE metric. Okay, so what do I mean by refinement? So this invariant has only two values, 1 or 0. That's why it's Z2 valued. Whereas the Yamabe invariant is a real valued. It's producing a real number. So what do I mean by a refinement? So I mean that if P of M1 is not equal to P of M2, that is, if P can be used to distinguish these two manifolds, then the Yamabe invariant is also different. So if two manifolds can be distinguished using P, they can also be distinguished using the Yamabe invariant. However, the Yamabe invariant is better in the sense that there are manifolds which P cannot distinguish that the Yamabe invariant can. So you could have two smooth manifolds and you know somehow they're homeomorphic, but you really want to know, are they diffeomorphic? Well, you could maybe use this invariant P. You could check, okay, they either both have positive scalar curvature or they both don't have positive scalar curvature. So P will be the same for both manifolds. However, the Yamabe invariant is more delicate. It has more information. And I can show that, well, in this example, the Yamabe invariant is, say, 0. And this example, the Yamabe invariant is less than 0. So even though they both fail to have positive scalar curvature, the Yamabe invariants are different. So they're not diffeomorphic. Yeah, so these examples aren't easy to come up with, but they exist. So the takeaway is that this Yamabe invariant is an even stronger invariant than this one. Okay. So I'm almost done. So let me just say a last few things about this Yamabe invariant to give you some information. So if the Yamabe invariant is less than or equal to 0, then it is equal to the supremum of the values of constant scalar curvature metrics. If it's positive, that's not true anymore because there are constant scalar curvature metrics which aren't Yamabe metrics. But if you replace constant scalar curvature with Yamabe, it is true. Okay, so the sign doesn't change with this definition, but the value will. Okay. So if you know that you don't have positive scalar curvature, you can just look at this set of constant scalar curvature metrics, and that's enough to compute the Yamabe invariant. Let me mention one example of a value you can compute. So by Urban, we know that if you take any conformal class on the sphere or any manifold, the Yamabe constant is less than the one you get of the round metric. So in particular, y of m, which is the supremum over all conformal classes, sorry, y of the sphere, which is the supremum over all conformal classes, that's equal to it just has to be equal to that of the conformal class of the round metric. Now, as the round metric is Einstein, in fact, constant sectional curvature, so in particular Einstein, we can compute this constant as just the value of the functional of that metric. So this is by theorem of Obata that I mentioned before. Okay. So this allows us to actually compute the value of the Yamabe invariant of a sphere. So the Yamabe invariant of a sphere is equal to the Yamabe constant of the round metric, which is equal to the value of the functional of that metric, which if you do an integration is n times n minus 1 times the volume of the sphere with respect to this metric to the power of n over 2. And there is an expression for this volume in terms of the gamma function of n over 2, okay, and powers of pi. So you can easily find that, but you can actually compute this value explicitly. Okay, but in general, it's a hard thing to compute. But here, there's kind of enough special about the sphere that you can actually say the precise value. And as we saw before, if you take any other n-dimensional manifold, its Yamabe invariant will be less than or equal to this. So we say, so now in this case, the Yamabe invariant was just equal to the value of the functional of some metric. So we say G realizes y of m if G is a Yamabe metric with y of m equal to E of G. Okay, so in this case, we would say the round metric realizes the Yamabe invariant because it is a Yamabe metric whose normalized Einstein-Hilbert functional value is equal to the Yamabe invariant itself. So it's a metric which realizes that value. Okay, so conjecture, if G realizes y of m, then G is Einstein. Okay. So let me draw a picture. This will be one of the last things I do today. Okay, so I'm thinking of this here is my space of Riemannian metrics on my manifold M. And I've got these equivalence classes inside of this manifold, which are the conformal classes of my metrics. So I'm going to draw them like this. So the blue lines here are my conformal classes. Okay, so these are my conformal classes. And then within each conformal class, there's a Yamabe metric, which minimizes the value of the Einstein-Hilbert functional. So I'm going to indicate them by a red dot. Yeah. And so, okay, so I think of, in this picture, I'm thinking of this functional as just the height. So within a conformal class, I'm taking a minimum, and then I'm taking a supremum of the minimums. So the thing you should visualize is that I'm kind of getting towards a saddle point. Right? So this kind of, if G realizes y of m, we think of it as kind of like a metric right at the top here at this saddle point. And remember, we saw before that Hilbert showed that the critical points of this functional are Einstein metrics, and a saddle point should be a critical point. Okay, so this conjecture isn't quite proved, but it's basically proved except for one case, which relies on positive scalar curvature. So basically, if you don't have positive scalar curvature, it's true. But if you do have positive scalar curvature, there's a technical difficulty, which is kind of very representative of a lot of questions in this field. Basically, if you don't have positive scalar curvature, things work out easily. If you do have positive scalar curvature, it's harder. Okay, so there's more I could say about this, but let me say one last thing and then I'll stop. So this is a surprising theorem. So as I've kind of maybe alluded to, this is really difficult to calculate in general. It's just very difficult. There's a lot of information that goes on. Okay, but here's one fact due to Petian, 2000. M is closed, smooth manifold, simply connected, and dimension is at least 5, then the Yamabe invariant is greater than or equal to 0. So this is also true if dimension of M equals 2 or 3, but not if dimension of M equals 4. So as we'll see later on, there are simply connected 4 manifolds which have negative Yamabe invariant, but that's somehow special to dimension 4. It doesn't happen in any other dimension. So, okay, so I think there's much more I could say about the Yamabe invariant, but basically the takeaway is it's an invariant that's defined on any smooth manifold. It's built up out of Riemannian metrics. It's positive if and only if you have positive scalar curvature, and it's very difficult to compute. But as we'll see, it's somehow interesting from the point of view of the question we were trying to answer at the beginning. So next time I'll talk about kind of the complex geometric side of things. What's the Kadara dimension? What are complex surfaces? What's their classification? And then in the following lectures, we'll see, well, what's the relationship between this strange invariant and the Kadara dimension? And we'll see that it's not completely arbitrary. There is some relationship there, which is maybe surprising. Okay, I think I'll stop there.
All right, very nice detailed introduction with nice pictures. Thank you very much.
All right.
Any question?
I got the questions.
Okay.
In your example, SN cross TM, what is Yamabe metric on there?
Oh, that's a good question. I don't know explicitly what the Yamabe metric is. I just know that these ones won't be. So it's an interesting question. Let's see. It's after one. Yeah. So yeah, your question is, well, these metrics I've constructed, HT, you can show that they're not Yamabe metrics. But the question is, what are the Yamabe metrics? I don't know. I don't know explicitly if you can find what the Yamabe metrics are. That's a very interesting question.
Thank you.
No worries.
Any other question? All right, thank you very much for the nice talk.